My name is Untitled. I'm a data scientist in Anodot, and today I will tell you why a spike in sales is not always good news, and why is it so important to find the relationships between time series metrics at scale. So we start with an example from e-commerce. Let's say that I have an e-commerce company which sells different products online, and I see that there is a sudden increase in the number of orders of these sunglasses. Great, isn't it? So sometimes it is good. Looking at some other measurements, I see that the revenue is also increasing accordingly. But I want to understand why it's happening. So looking further, I find out that Wonder Woman Gal Gadot just posted this image in her Instagram. So my sunglasses became very popular. Understanding this is very valuable opportunity because I can immediately take action items and make sure I have enough of these sunglasses in stock. But sometimes spikes in sales are not good news. And let's look at the following scenario. Again, I have a sudden number of orders of these sunglasses, but when looking, if I only look at the number of orders, I may think that everything is okay. But when I start to look on other measurements, I see that the revenue is not increasing as expected. And I can't find any event to justify this increase. Looking further on more measurements from different sources, I find that there is a growth in the number of mentions of my application, of my company in Twitter. So go to Twitter to see what people are saying about me, and bingo, I have a glitch in my website. I'm selling these sunglasses for $2 instead of $50 by mistake. By crossing information from different sources, I can get the full picture and understand what is really going on here. So the stories I just told you are totally hypothetical, okay? But glitches and breakdowns and opportunities you don't want to miss happen all the time for all the companies. So here are just a few such examples that were published. Amazon web servers were down and caused problems all over the network. And United Airlines sold super cheap first-class tickets by mistakes. And there are many such stories. The common thing about them is that without crossing information from different sources, it is very hard to understand that there is a problem and to understand the full picture of what is really happening. Many things can cause breakdowns and slowdowns or opportunities. So for example, partner changes. If I have a new partner integration, then it can lead to slowdowns in my application, but also to new opportunities. Device changes, such as operation system updates and new devices. External changes, such as media coverage and holidays and competitive strategy changes. Company changes, such as new version deployment and promotions, all can lead to changes. In order to track changes, businesses are collecting many metrics over time. By detecting the abnormal behavior of a single metric, we can understand that something is wrong with it. But univariate anomaly detection creates alert storm. When such an event occurs, often there are anomalies in many other related metrics. Each KPI has dozens of other KPIs relates to. By grouping related anomalies, we can make order in the storm of alerts and get the full picture of what is happening, as we've seen in the previous examples. So we understand that it's important to find the relationships between different metrics. And how do we do multivariate anomaly detection? The way we do it is we start by collecting many metrics over the time. Now, businesses may collect millions of metrics. Next, we learn the normal behavior of each metric separately using time series analysis techniques. Once we have the normal behavior model, we can detect abnormal behavior for each metric separately. Next step is to learn the behavioral topology between the different metrics, the relationships between the different metrics, and that's what I'm going to talk about most of this lecture. Finally, we can collect feedback about the anomalies and the relationships that we've detected and feed them back into our learning mechanism. In this lecture, I will talk about 3 types of similarity: name similarity, normal behavior similarity, and abnormal behavior similarity, and I will show how it can scale to millions. So I'll start by explaining the full procedure of finding name similarity, including how to scale it with LSH algorithm, and then I will show how it can be modified to the other types of similarity. So let's start with name similarity. Metrics are not just numbers, they have names too. And here is a metric. It counts the number of shoes purchased by users in England using their iOS-based mobile devices. Now, the name of the metric describes what it measures, the purchase count, and where it was measured, the product family, the country, device type, operation system, and so on. As an e-commerce, I may collect millions of such metrics with different measures. It can be purchase count, but also revenue or price or anything else. Different products, different countries, different devices, and so on. The names of the metrics are a hint for the relationships between them. So, for example, the number of shoes sold to users in England using their iOS mobile device is probably related to their average price. So the names of the metrics are a strong, the similarity between the names of the metrics is a strong indication of the relationship between them. How can we measure the similarity between 2 metrics? So given 2 metric names, in this case we have 2 metrics with 5 properties each, including the what we do is we calculate the cousin similarity between them. So we count the number of shared property values. In this case, we have 3 shared properties: the country, the device type, and the operating system. And we divide it by the norms of the metric names. So if each metric has 5 properties, we divide it by square root of 5 multiplied by square root of 5, which is 5, of course. If the similarity is bigger than some threshold, then the 2 metrics are similar. But some properties are more common than others. So, for example, if all the sales are made in England, then the more common properties bias the similarity score. So we want to give less weight to common properties and more weight to rare properties, which actually distinguish the metrics. What we do in order to weight the property values is we can use IDF, inverse document frequency, so that the weight of the property value will be how much it is common in all of the metrics. So the IDF of a property value is the number of metrics with this property divided by the number of metrics, and we take minus log of this, so that the more frequent the property, the lower is its weight. So now that we have the weights of all of the property values, we can represent each metric name as a vector, as follows. So first, we build a dictionary of all the property values that we have in all our metrics. So this dictionary will contain a purchase count and also average price. It will contain shoes as product family and product family shirts and England and so on. Now, for each metric will be converted to a sparse vector representation in the size of the dictionary. So each of our property values in the dictionary will have a corresponding entry in this sparse vector. Given a metric name, each of its properties, in each of its property values entries in the sparse vector, we put the IDF weight of these property values, and for the rest of the entries, we put 0. So in this example, for purchase count, we will put the IDF of purchase count, and the rest of the what properties will be 0. We put the IDF of England in the right location, and 0 for the rest, and so on. So now we have a sparse vector representation for each of our metric names. And now calculating the cause and similarity is a simple operations on vectors. So we know how to calculate similarities between two metrics, but a business may have millions of metrics. Now 1 million metrics induce about 10 to the 12 pairs of metrics, and we can't calculate, it's infeasible to calculate the similarity between all of them, even using advanced pruning techniques. One solution is to use LSH algorithm, local sensitivity hashing. Now, I won't get into the details of this algorithm, but basically the idea is that for each of our metrics, we calculate a hash code, so that if two metrics are similar, with very high probability, their hash codes will be identical. Now, I know it sounds like magic, but there is a lot of theory behind LSH, and it actually works when using hashing methods based on random projection, and we need our vectors to be sparse. Okay, so all the metrics that got the same hash code, that are in the same hash group, are candidates of being similar. And we only need to calculate exact similarities between them. In Anodot, this procedure reduced the computation by orders of magnitude. Let's summarize the procedure of how we calculate normal similarity. Name similarity, excuse me. So first we create an ordered dictionary of property values from all our metrics. We compute the IDF weight of each of these property values pairs. We create a sparse vector representation of each metric in the size of the dictionary. We compute the hashes of each of these vectors, and for each hash group, we calculate the exact similarities between its members. So far, we talked about name similarity. Now let me explain how to modify this process to other types of similarity, and we start with abnormal similarity. When two metrics are often abnormal together, they have many overlapping anomalies at the same time, we assume that they are related. So, for example, I guess that many of you have kids or had kids in kindergarten. Now, when one kid gets sick, what happens? Very soon, all of the kids in the kindergarten will get sick as well, right? Now, I know that some of you will tell me that this is not an anomaly. I know, but you got my point. So if two metrics are unrelated, they're totally independent, the probability that they will have overlapping anomalies is getting lower and lower as the more anomalies they have. This is why it's important to find abnormal similarity. The procedure of calculating abnormal similarity is almost identical to the procedure of name similarity. The only difference is in the way we calculate the sparse vector representation. So how do we do that? We discover anomalies in each of the metrics for a fixed period, say last 90 days. Now we represent each of the metric anomalies in a binary sparse vector. so that whenever this metric is abnormal, we put 1 in this vector, and whenever it's normal, we put 0. Next steps are exactly the same as we did for name correlation, name similarity. We compute the hashes of each of the transformed time series, and for each hash group, we compute the exact similarities between its members. Another alternative, which is applicable for other types of similarity as well, is instead of calculating the similarities between each pairs in a hash group, we can run a clustering algorithm within each hash group, such as LDA, and we use the similarity as the distance measure. And this is sometimes very useful because we often more interested in groups of similar metrics and not just pairs. Normal behavior similarity. So if two metrics behave similarly, they have similar patterns, then we can assume that they are correlated. So just by looking at these examples, you can assume that those 3 metrics, the first 3 metrics, are probably correlated, and maybe also the last one. So it's very trivial to understand why we need it, but computing the normal behavior similarity is not so simple. One way to do it is to use various types of linear correlation methods, such as Pearson correlation or cross correlation, if there can be lag between the metrics. But linear methods are very problematic in several aspects. So they are very sensitive to trends and to seasonal patterns. And even after removing these, after we do deseasoning and detrending, it still doesn't work. They are also sensitive to scale, so that if 2 metrics are very, very different, like you can see here, those 2 metrics are very different most of the time. But in a very small period with extremely high values, they are similar. This small period may bias the whole similarity between them. So in this specific example, the similarity is almost 0.99, which is very, very, very high. So we tried, we did experiments on linear methods. We tried several tricking and tricking, and we always, the results were, always had too many false positive and too many false negative to our needs. It just didn't work. Another problem is scaling. Because if we use the values, the original values of the metrics as is, it is impossible to get sparse vector representation. As you remember, in order to use LSH to scale, we must have sparse vector representation or low dimensional representation. But in this case, we always, it's impossible to avoid high dimensional dense vectors. So for example, 90 days of hourly sampling interval induce vectors of size 2,160, which is way too much. How can we get a sparse or low dimensional vector representation for each of our metrics? So instead of looking at a metric as a sequence of values, we can look at this metric as a sequence of patterns. So if you look at this example here, I hope you see it, then it can be viewed as a spike, then a straight line, straight line, straight line, spike, straight line, and so on. So what we can do is we can create a pattern dictionary. And then we use our pattern matching engine in order to represent each of our metrics using those patterns. So instead of we convert each metric original values to a sequence of patterns. Now this representation is sparse or low dimensional depending on the implementation. So it's good for us because it's amenable to regular clustering and similarity methods. We can use the same procedure as we did for name correlation and abnormal correlation. And we can use IDF to weight the patterns so that common patterns will get lower weights and rare patterns will get higher weights. How can we create a dictionary of patterns? One way to do it is using deep learning. Now, I'm not going to get into the details of this. I just want you to get the general idea. So what you can do is you can train a stacked autoencoder network with many time series. So the input of this network will be the values of the matrix, x1, x2, x3, etc. After some pre-processing, including normalization, de-seasoning, detrending, and so on. And the output will be the patterns of this metric. Once we have our network trained, we can use it to convert each of our metrics into their new sparse representation based on patterns. And now we can run our procedure to compute similarities between them and use LSH on these sparse vectors. Now, just a slide to demonstrate how valuable this is for Anodot, for my company. So here are some weekly statistics that we collected. We collected 230 million metrics over this week. We detected from them 260,000 anomalies. 25,000 of them are significant anomalies with high scores. And after using our similarity procedure, we were able to reduce this number to 4,700 correlated incidents of anomalies. And some other numbers. These are statistics of monthly metrics collected over a month. So over a month, we calculated around 350 million abnormal correlations, 430 million normal correlations, 370 million name correlations. So overall, 1 billion correlations a month. So to summarize, we've seen that it's very important to find relationships between different metrics. It is used to make order and cluster anomalies. So this way we can reduce the number of incidents of anomalies, and we can identify and analyze problems or opportunities. Another thing that we can do with by knowing the relationship between metrics is prediction. So if I know that the sales of a product are increasing, then I can predict that the sales of another related product will also increase or decrease accordingly. And if I know that a kid in the kindergarten of my son is sick, I can predict that within a day or two, my son will get sick as well. Thank you very much. For further questions, you are welcome to email me to inbal@anodot.com. Any questions? Okay. Thank you.